For pretty much the rest of this unit, we're going to be talking about black holes. And I'm going to do a lot of lectures on black holes because I think black holes are, first off, one of the most interesting things we can possibly study in astronomy. And also because there's a lot of interesting physics that we can study with black holes. They're cool just in and of themselves, and black holes are a really awesome topic. But the physics is also pretty useful to understand. We can learn a lot about gravity by studying black holes, which some people would say are just like pure naked gravity. Gravity just by itself, that's what a black hole is. Actually, the most common definition that you're going to see of a black hole is that it is an object that has so much gravity that nothing can escape from it, not even light. You wouldn't ordinarily think about light as something that is affected by gravity, because the amounts of gravity that we deal with in most ordinary situations, even in astronomy, are not big enough to have a huge effect on light. But it turns out that gravity actually does affect light, and we'll talk a little bit more in a minute about what does this mean that light cannot escape from a black hole. But first I'm going to talk about where do black holes come from. And the concept here is that this is another possible endpoint for the life of a star. We talked about low mass stars like the sun end their lives as white dwarfs. And in the last couple of lectures, we talked about sort of pretty high mass stars, but not the biggest ones. And those end up as neutron stars. But we also may remember that there was a limit to the mass of a neutron star. That if you get more than 3 solar masses in a neutron star, even neutron degeneracy pressure is not enough to support it against gravity. So if we take the most massive stars, who start off with at least, let's say, 8 times the mass of the sun, and that have a core that's bigger than 3 times the mass of the sun, after the supernova, the core becomes a black hole. Again, that 3 times the mass of the sun for the core is the limit that comes in because that's what neutron degeneracy pressure can support. But if you get bigger than 3, neutron degeneracy pressure can't support it, and so it collapses further and becomes a black hole. So that's where these things come from. And I want to talk a little bit more about what does this mean that light can't escape from it. What is that talking about? And to understand this, we need to know about something called escape velocity. And escape velocity is something that people who are interested in space travel deal with all the time. It's the velocity that you need to have in order to escape from the gravity of a larger object. So for instance, let's say you want to send a rocket from the Earth to the moon. Or better yet, let's say we want to send one from the Earth to Mars. Well, if we want to get from the Earth to Mars, we have to get away from Earth first. Earth has a lot of gravity, and it's going to try to pull that rocket back down. But if I go fast enough, I can escape from the Earth's gravity and then fly through space and eventually get to Mars. You have to escape from the gravity of the planet you're starting with in order to get to a different one. And there's a formula for the escape velocity, which is this formula right here. And that it says that the escape velocity is the square root of 2gm over r. G is the gravitational constant, 6.67 times 10 to the negative 11. You learned about this in physics last year when you studied Newton's law of gravity, and you may even have this programmed into your calculator as G. If it's not and you would like it to be, come talk to me. M is the mass of the thing you're trying to escape from. So, like in this little picture here, you're trying to escape from Earth. Eventually that's going to be our black hole. And r is the radius of that object. So it makes sense that if the mass of the object is bigger, you have to be going faster to escape it. It also turns out that if you have a smaller radius object, you have to go faster to escape from it, because a smaller radius object has more gravity. Gravity is really more a function of how dense something is, how much mass there is within a certain volume. And so the radius becomes important as well. And the smaller something is, if you take the same amount of mass and cram it into a smaller space, it has more gravity. So that's what the radius is doing in here. If you're trying to think about escape velocity, this little picture is saying, okay, let's say I have this gigantic cannon that I'm sitting on some mountain at the North Pole, which there is no such thing, but okay, let's pretend. If I don't fire it very hard, it just falls straight back down. If I fire it a little bit harder, if I shoot it more like a missile, I can maybe send it somewhere over the Pacific Ocean. If I really fire it hard, I can get it even into a different hemisphere. At a certain point, if I fire it hard enough, it actually will keep going in orbit around Earth. And that's what these other ones are doing. And eventually you get enough speed that it just doesn't come back down and it just escapes altogether. Now, a black hole is defined to be an object whose escape velocity is greater than or equal to the speed of light. So, light is the fastest thing there is. The speed of light is the greatest possible speed. That's one of Einstein's big conclusions, is that the speed of light is the fastest speed there is. Nothing can travel faster than the speed of light. So if your escape velocity is bigger than the speed of light, then light can't escape from it. Light's not going fast enough to escape from it, and nothing can be going faster than the speed of light, so nothing can escape from it. That's what it means to say nothing can escape from a black hole, not even light. Nothing can get out of it. Once you are in a black hole, there is no coming out. It's not possible. That's what it means to be a black hole. Nothing will ever come out, which is kind of interesting because that also means that no information can ever get out. So let's say your crazy friend decides to jump into a black hole, and let's say he has something that's going to enable him to survive this, which is not very likely, but he says, I'm going to radio a signal back out to you once I'm inside, let you know that I'm still alive. Well, his signal is traveling at the speed of light. That's not fast enough to escape from a black hole. It just falls back down, kind of like these wimpy cannonballs do. It just falls straight back down inside. Even light, even a radio signal, falls straight back down. Just to show you a little bit of how the math works, you may want to go to your packet and look at problem number 5. So we're just going to figure out the escape velocity of Mars, just so you can see how this kind of deal works. So I looked up in Appendix E the mass of Mars, which is 6.42 times 10 to the 23rd, and it said that the radius of Mars is 3,397 kilometers. I'm going to convert that to meters. You want, when you use the escape velocity formula, to have everything in kilograms, meters, and seconds. It has to be, because that constant g is in there. You have to do it that way. So then I'm going to use my escape velocity formula. There it is. And I can plug things in to the escape velocity formula. So I'm just going to leave g as g. I've got that programmed into my calculator. It's a constant. And there's the mass and the radius. And you're going to do this whole division and then take the square root. If you're trying to do this for yourself, which is a really good idea, do all of the division first and then take the square root, and you should get an answer of about 5,020 meters per second. So that is several miles per second. For Earth, it's something more like 11,000 meters per second. So you have to be going very, very, very fast to escape from something the size of a planet. But on the other hand, that's nowhere near the speed of light, which is 300 million meters per second. So clearly, Earth and Mars are not black holes. Things can escape from them, you just have to have a rocket to do it.